First, let me thank the organizers for inviting me to this workshop. And it's my first time at IMSC. So it's a very small but pretty campus, very pretty campus that I found here. And I'm very glad that I had decided to come here to attend the workshop. So the topic that I would be discussing with you today for the next 35-40 minutes is about multi-messenger astrophysics using high-energy photons and neutrinos. So 2017 is a year, I fondly call it a year of the multi-messenger events, primarily because it made a big splash in the world, that the first binary star neutron star merger of electromagnetic counterpart of the gravitational wave was seen, and that made a huge splash in the whole world. But in the same year, a somewhat little minor event got slightly overshadowed probably by the big event of the gravitational waves, was the first detection of high energy neutrino coming from an astrophysical source, and in correlation with very high energy gamma rays and very high energy gamma rays from that same source. So, and that would be the major part of what I would discuss today, and then also certain follow-ups of that. So what astronomers normally do is that they send out telegrams when something interesting happens, when they see something interesting happening. So these are kind of astronomers' telegram, which are just short bursts of information so that other telescopes can react to it within a very short amount of time. So that's the first two telegrams that came out before even when IceCube actually sent out an alert that they have seen a neutrino of a very high energy, and we'll come to all that in the next slides. Fermilat, which is a gamma ray telescope at medium energies operating at few 100 MeV to few GeVs or few tens of GeVs, detected an increased gamma ray activity from a certain blazar, and I'll come to again to all of these, located within the IceCube error region. And a few days later, there was very high energy gamma rays detected by MAGIC from the direction consistent with this IceCube neutrino. So that would be the main part of the talk that started the multi-messenger field using neutrinos and photons. And the primary motivation to do all of that is to look for sources of cosmic rays and to understand the origin of cosmic rays. So most of it I would kind of stick to neutrinos and gamma rays, but I would also show you at some part of the talk that even at lower energies, optical and X-rays are also very important in understanding these objects. So you already know that the origin of cosmic rays cannot be done only using just charged particle astronomy, simply because these cosmic rays get deflected in the magnetic field and then they lose their apparent source direction. However, if there is matter around these sources, they would emit gamma rays or neutrinos, and using gamma rays and neutrinos, you could actually point back to the sources. So what is important is spatial and temporal correlations between neutrinos and gamma rays can trace cosmic ray acceleration sites. However, you could argue that you could have done this only with gamma rays. That is what I started doing several years ago as a PhD student and a postdoc. And there you would have to we were trying to distinguish between two different types of acceleration mechanisms that you would see. One is the leptonic acceleration, where there would be electrons in the magnetic field. They would produce synchrotron radiation that would produce the first part of the spectrum, and then those synchrotron photons will be upscattered to TeV gamma rays through an inverse Compton effect by the same set of electrons that are present in the system, and there you would see this inverse Compton spectrum in the high energy gamma rays. And then there could be hadronic acceleration, where protons would interact with matter, produce pi zeros, and then pi plus and pi minus. The neutral pions would decay into TeV gamma rays, and then they would have certain distinct spectral shape. So one thought that at that time that if you had data all over the spectral energy, what you call the spectral energy distribution, you should be able to distinguish between the two acceleration mechanisms. It turned out that this is just a cartoon, and the life is much more complicated than that, because there would be also lower energy cascades which would modify all the spectrum, and then the distinguishability is not that apparent. Hence came the neutrinos, so because they've start to become then the smoking guns for hadronic accelerators. I don't need to talk too much about ice cube detector. Most of you again know about it, that it's a kilometer cube detector in ice in the South Pole, where they have these digital optical module systems, many thousands of them deployed in ice down to almost 2.5 kilometers from the surface of the ice level. At the top of the ice, there they have an air shower array called the ice top. And so IceCube has been deployed. All these 86 strings and all these digital modules have been deployed over several years. And by 2011-12, they completed the whole array and has been taking data since then. Now, so what one does is that a neutrino infrequently would interact in the ice and then produce a nuclear reaction, and then would produce muons. And these muons can travel kilometers in ice, and they produce Cherenkov light as they move with speeds greater than the speed of light in that medium. And these optical sensors catch and map this light. And from that, you get an idea of the energy, you get an idea of the direction. Once you get an idea of the energy and the direction, you can start to think about doing astronomy with it. Okay, so quite early, even before IceCube, when the smaller detector called the Amanda was in place, we had started to think about doing these neutrino, what we call TO is a target of opportunity program. So for example, if you see at least a very energetic neutrino or a cluster of neutrinos coming from a certain direction in sky, you would send triggers to electromagnetic telescopes like these gamma ray telescopes like MAGIC, or the high energy gamma ray telescopes which are ground based ones. So we started developing this NTO program way back in 2007. The first alerts were sent around that time. At that time we were calculating what would be the kind of alert rates, what would be the false alarm rates and all that. And then this was well tested by 2010, and then they were put in place. However, IceCube had not seen many neutrinos at that time, so it was, and then many revisions took place over the years. And now what happens is that IceCube kind of sends out real-time alerts. Since April 2016, they have been releasing these real-time alerts of detection of high-energy neutrinos, especially greater than 100 TeV. And then one could start to search for neutrinos correlated with gamma ray sources. Primarily, these are blazars, where these are objects which are extragalactic sources, active galactic nuclei, where the radiation is pointed towards the Earth. There have been sporadic claims initially, but there was no clear detection till 2017. Here you see a kind of list of what they would send out as alerts. They would give you the energy information, they would give you the time when this alert was sent out or when the event was detected. They would tell you from which direction in the sky it came, the right ascension and the declination. They would also tell you what is the angular resolution of that event. And then they would also give you a classification of what sort of topology this event is, whether it's a shower-like event, whether it's a track-like event, these kind of topologies you would send out. And I'll tell you why this topology is also very important. Now, this alert system has been upgraded in 2019, so IceCube kind of did away with their old system, which we were working many years ago, and now they have a system in place where they classify a probability of each alert to be of what sort of an astrophysical origin. So if it is of 30% astrophysical probability, it's called a bronze alert. If it's a 50% astrophysical probability, it's called a gold alert, which is like a purity of the signal that you want to say, that how pure this astrophysical signal is. And this is publicly distributed via what is called the Astrophysical Multimessenger Observatory Network, which is AMON, or a global network, so that the follow-up observations by other electromagnetic telescopes can take place. And again, the aim is to identify a possible electromagnetic counterpart. Then there is a second stream of alerts which IceCube also gives out, which is private alerts. These are not publicly distributed to the whole world. So they have certain MOUs in place with the electromagnetic telescopes. And for example, like MAGIC and Veritas since 2012, in the southern sky, the Hess Observatory in 2019. So they have a list. So these observatories prepare a list of sources based on their flux variability, based on their spectral shapes, and those which could become plausible neutrino emitters, and those source list is followed by IceCube, and then if some neutrinos, excess neutrinos come from some of these sources, then they send out these alerts as a private information. However, from October 2024, IceCube has decided to discontinue the private alerts and make them all public. And so we are now currently discussing preparation of a new source list for these alerts to come out. Okay, so now the important question is that which are these types of events important for as target of opportunity events for electromagnetic telescopes? So the field of view of these electromagnetic telescopes, gamma ray telescopes especially, are small and narrow. So they are typically of the order of between 3 degrees to 5 degrees. So they are pointed instruments. So you need to have good angular resolution for these telescopes, so for the triggers to come in. So hence, those ones which are really cascade events from IceCube cannot be followed up by the electromagnetic telescopes efficiently, because the cascade events have an angular resolution of almost about 10 to 15 degrees, sometimes a little better, but the average one is about 10 degrees. So within 10 degrees, your field of view is 5 degrees, you can only make a scan, but you cannot do much better than that. So the best events that you have to select are those trap events where the typical angular resolution is at the order of a degree or even better than that. So only muon track events are generally used to follow up observations in the small field of view. So now let me come to the actual the scientific observations that on September 22nd in 2017, so through this AMON or GCN, IceCube sent out an alert that they had seen a high energetic neutrino, muon neutrino. And then and they alerted all the observatories and wanted them to follow this up because this was a very clean event and possibly of high astrophysical origin. And then on September 27th, Fermilab collaboration, which was following this up, found out that there is a blazar in the error circle of IceCube, very close to the best fit location of IceCube, which also showed brightening in the GeV gamma ray band. And this was the telegram which I was hinting at the very first slide. They sent out an ATEL, the telegram sent out by Fermilab, and then many other observatories started observing. MAGIC started observing already after getting the IceCube alert around 24th of September, and slowly MAGIC also saw a flare in VHE gamma rays. And then there were several other observatories alerted. So in the next days, you can see here a flurry of astronomers' telegrams kept on coming, most of them having seen flux variability in various other wavelengths from this source. Okay. So this is the kind of the MAGIC light curve, and other observatories like Veritas and MAGIC. Veritas initially did not see any emission, but later on they started to see emission also, primarily because this is a faraway redshift source, which makes it better for MAGIC, which is a larger telescope, to collect more photons in lower energies, and Veritas, being a smaller detector, does not collect that many number of photons. So they were statistically not seeing significant signal till they could integrate data over a certain period of time. So this is the kind of the light curve. So it's the flux as a function of time. And now I'm going to show you what the source was doing around the IceCube or before the IceCube alert. So this is the IceCube alert came. This is the kind of the flux variation a source, a kind of these type of sources. So show when over a longer period of time, and you can see that during the IceCube alert there was, or even slightly before the IceCube alert came, the flux had already started to rise up. This was after the alert. In MAGIC, for example, when you see that initially we did not see much of a signal, but then again we started to see the flux rising, and then slowly it decayed. And then we carried on making more observations, and then we also saw variability in gamma rays much later period when there was also no IceCube neutrinos. The neutrinos were not detected then that time. So the first thing is to understand whether there is a spatial correlation between these things or not. So a joint analysis was done using a likelihood ratio test, and you calculate a chance probability. You estimate it through this, which you estimate through this likelihood ratio test, and you disfavor the fact that this is just due to a fluctuation, that these are correlated just by fluctuation. You discover at about a 3 sigma level. The energy of the neutrino was computed to be pretty high, about almost 300. Maximum energy, or the most probable energy is about 300 TeV, with a lower limit of about 180 TeV and an upper limit of about 4.5 TeV. This all depends upon what sort of spectrum that you would assume in your Monte Carlo to derive the energy spectrum. And this is again the long-term light curve of the various observatories which we will go and find out. So this is the trigger. This is what it was doing in there were very few observations done on this source before IceCube really gave out the trigger, simply because this was not a source which was expected to emit very high energy gamma rays, because it is at a quite a large redshift. When you have a source at very large redshift and if it is throwing out high energy gamma rays, you don't observe it simply because there is a gamma ray horizon. They interact with the extragalactic background light, the light which comes from all the stars and galaxies integrated over in your line of sight, and then the gamma-gamma pair production would take place. So you define what is called an optical depth, and that so you have the observed flux, which is the intrinsic flux multiplied by an exponential function, which is an optical depth dependent upon the redshift of the source and the energy of the photons that are coming from the source. So initially we did not do many observations at very high energies because this was not really expected to emit very high energy gamma rays. But in Fermilab, which is a lower energy detector, GeV detector, you expect, so there are lots of data on Fermilab, and then you can see right before or around the IceCube trigger there is a flare. In MAGIC one showed, or in other high energy gamma ray telescopes there was a flare after the IceCube, and then there are other wavelengths like X-rays and optical, where you try to understand the long-term behavior of the source before you start to go and do any sort of modeling with this. So before or after the flare, there was not much change in the spectral shapes seen. So there was no clear spectral variability. So a simple power law would also fit very well the data with an exponential cutoff. That is what I was hinting before, that if you have a certain source at a high redshift, then depending upon where your source is, what redshift, the photons of that energy will get attenuated, and you start to see curvatures in your spectrum. So higher the redshift, earlier the source starts to cut off. The lower the redshift, the source starts to cut off at a lower redshift. So this source was at a redshift about 0.34. So 0.34, you can, here I don't have the redshift, but 0.34, so this is at redshift of 0.5, you already see it's starting to show cutoff below 100 GeV. So that's why it was high energy gamma ray telescopes were not expected to see this source quickly. There were observations also carried out in X-rays or radio, optical, in various other wavelengths. So this kind of shows the long-term behavior again. So there was enhancement of flux in radio also seen quite a bit after almost 2 weeks after the alert was sent. But then radio comes from much bigger regions, because these sources are powered by supermassive black holes, and they have jets in the system, and then the radio is far down the jet. So you do not expect radio emission immediately coming very close to the black hole, or close from where you do expect emission to come from either neutrinos or high energy photons. So that's quite consistent that you would see excess quite.
And this is some even that tells us that it became.
The neutrino is just one. The neutrino is just one muon neutrino of 300 TeV energy. But the electromagnetic, yes, the electromagnetic emission has been going on for quite some time. And I'll show you what the implications of that means. So now, remember the earlier plot where I was talking about the spectral energy distribution, that if you put all these data together, you would then start to do modeling and then expect that you would be able to distinguish between the different acceleration mechanisms. This is the same plot I come back here, where you now see that all these kind of data have been put together, and now then people, so there were an explosion of theoretical papers in the archive once you start to put in all the data in the next days. So people started using various types of hadronic models, including leptohadronic models, pure hadronic models, photohadronic models. All these kind of models start to come in to the picture. to try to explain the whole spectrum. In fact, one of these guys like Shan Gao and their collaborators, they even showed that even a pure leptonic model would fit the data quite well. So you do not really, even if IceCube had not detected neutrinos, you would be able to see, explain the whole multi-wavelength photon behavior of that. So they did not, they said that there was no need for any neutrinos in order to model the source. However, they could say that since IceCube has detected neutrinos in spatial correlation, however, we do not know whether the temporal correlation is really correct or not, but using models or the suitable model parameters, you could explain the leptohadronic model and put an idea about how much of the hadronic contribution would be there in order to explain the IceCube data. And for that, I told you before that X-rays also would play an important role, especially because when we worked on it, what we showed is that this event would also cascade to lower energies, to hard X-rays or soft X-rays. And so certain bounds can be got from the X-ray data, from the hard X-ray data, so that you do not overproduce the amount of flux in either high energy gamma rays or in the neutrinos. Yeah. So certain constraints can come from the hard X-rays also. So therein lies the importance of not just having gamma ray observations, but also X-ray observations. Okay, something very interesting which came from IceCube was right after that is that then they went back into their archival data to look for excess neutrinos from exactly from the source TXS 0506, and they found out that independent of the 2017 flare, the high energy event and the flaring event in gamma rays, there was already an excess of events they found out in their archival data. And but however, the more interesting thing came out is that when they looked at Fermilab data, it did not coincide with any flaring activity in Fermilab. So this was the IceCube events when it was not doing anything in Fermilab, it was quite quiet during Fermilab. That threw you even more enigma to the whole thing, because then it raised the questions whether you really saw them in time correlation or not. So spatial correlation is well established, but time correlation you cannot really establish through that, because they saw once during gamma bright state and once during the gamma dim state. So it threw you up the question that whether they are really time correlated or not. Okay, so moving on to some more neutrino blazar coincidence stories. So then after this, there were a lot of other tentative correlation studies done with IceCube neutrinos, with blazars in their field of view. However, in the last 2, 3, 4 years, however, there had not been any significant detection in any other wavelengths with that. So the only one which we found which was quite interesting was another source, PKS 0735, which is even at a slightly higher redshift. And it raised the question whether it is associated with an IceCube event or not, because the source was not very close by, it was about 2 degrees away from the IceCube best fit location. However, we did study this source in quite some detail using multi-wavelength data, and there both Veritas collaboration and us, we together almost got out a paper, competing paper, but the conclusions were almost the same, that saying that you could actually constrain using hard X-rays from the constraints from the cascade emission. You need to use the hard X-rays. Veritas did not detect any high energy gamma rays from this source, unlike the one which was seen in TXS05. And of course, the question again, since it is even a larger redshift, there could be strong cutoff introduced due to the extragalactic background light, and hence gamma ray observations are not the most suitable ones in these kind of cases. Then there are some more. Now I move on to something slightly different. Then there are coincident subthreshold events between Hawk and IceCube. Hawk is a water Cherenkov detector, which has a wide angle field of view. So it kind of scans the sky. The sky passes over it. It's a static detector, not like exactly like a telescope. And so these are subthreshold events, are those where the single observatory would not have been able to detect the hotspots or detect excess events coming from using a single data from a single observatory. But if you do a joint analysis of these events, you could say something interesting or not. So that's why these are called subthreshold events. And then there is a joint program between HAWK and IceCube, where they select temporarily the IceCube events within the transit time of the sources in the HAWK hotspot, and then they do a statistic to rank the coincident events, and then the overlap of the spatial uncertainties are estimated through a maximum likelihood method. What they found out in their three or 4 years of data is that there were only 2 coincident events such found. However, this is quite agreeing with the background. So you need to compute what is your false alarm rate, and that comes to about 1.5 per year. So within 2 or 3 years, 2 coincident events is perfectly compatible with what you get from random fluctuations of the background. In fact, if I spend 30 more seconds on it, that I would also have to edit this slide almost online, because yesterday night there was such a coincident event sent out, and so we were discussing pretty late in the night whether to follow up with gamma ray observatories or not, simply because the exciting thing this time in this event was there is a Fermi-latch source sitting 0.1 degree away from the best fit location of both IceCube and HAWK. So that makes the life more interesting. So we'll see in the next days if we follow up with electromagnetic telescopes if something interesting comes out of it or not. So then there were also searches of neutrinos using hard X-ray sources, these active galactic nuclei. So these are motivated by environments where neutrinos can escape, but high energy gamma rays would interact either with matter or with low energy photons to cascade to lower energies. And so one looked at the X-ray catalog, which is a burst swift bat catalog, and then one performs a stacked search or an individual source search, and in that only there were 2 significant sources which were found out that could become significant in neutrino emission, NGC 1068 and NGC 4151. I'll come to NGC 1068 later, just in a minute or two. And there was no significant emissions shown from the non-blazar type AGNs. And then there is another very interesting work which was done in the last 2 or 3 years, is to understand how much of the contribution of the IceCube neutrinos are coming from blazars. So one looked at these guys, Guillaume et al. Looked at Fermi catalogs and various other catalogs, sources in the IceCube error region of 90% IceCube error region, selected very good track-like events, and they studied that, and then they constructed multi-wavelength spectral energy distributions, and they found out that about 20 gamma ray blazars in IceCube 90% error region could be potential candidates of IceCube neutrinos. This is at a post-trial significance of about 3 sigma or so. So they claim that there is a growing consensus that the blazars will be counterparts of at least a certain fraction of the IceCube neutrinos. Now, as I come to the NGC 1068, so over a 9-year period of integrated search, IceCube gave their sky map, and of which there are 3 sources which showed up above the background. The most significant of that was NGC 1068, which was at a global significance of just about 4 sigma or so. Then next came is another blazar, which is a PKS 1424, and TXS, which was the famous one which made all this story, was actually 3rd in its rank in that 9-year full rank. So this PKS 1424 is also quite an interesting object because it has been earlier detected in gamma rays by the Veritas collaboration. And NGC 1068 is a completely different class of object. It's a Seyfert galaxy. So the difference between these they are somewhat less luminous in nature than the quasars or the blazars, where the whole emission kind of outshine the whole host galaxy. So you cannot really identify the host galaxy. However, in these kind of objects which are called Seyfert galaxies, you can identify the host galaxies. They're somewhat less luminous in high energy radiation. Fermi-lat had detected gamma rays from this source. However, there has been no very high energy gamma ray emission detected from there. So when you again put up all these together, the multi-wavelength IceCube collaboration put all these multi-wavelength data together, and they concluded that the neutrino luminosity was about 1.5 times higher than that of the gamma ray luminosity using Fermi as the pivot. So I don't need to really rush to everything through. So some more later news in gamma rays and neutrinos. So now moving on from the extragalactic sky and coming to our own galaxy, the Milky Way galaxy. So this is how the Milky Way galaxy, our galaxy, looks like in various wavelengths, like in optical, in high energy gamma rays, in if there would be the pion decay, the gamma ray emission coming through neutral pion decay. And then this was what it was expected if there would be neutrinos also. And this is what the IceCube put out in 2023, where they found neutrinos from the Milky Way. However, they were using cascade events which have a larger angular resolution, so they cannot really point to what type of sources these are. At the same time, there is in China, there is a large air shower, high altitude air shower detector, which consists of hybrid detecting mechanisms like scintillators, water Cherenkov detectors, and even imaging atmospheric Cherenkov detectors. So it's one of the largest air shower arrays now in the world. And that LASSO had detected a large number of sources, about 12 of them, which they claim have emission, a gamma ray emission beyond 100 TeV. So all these are becoming potential, what we called pevatrons, that they can accelerate particles to PeV energies and beyond, and they become also potential candidates for neutrinos, neutrino emission. So then there was a study done a year back or so that about looking for neutrinos from the LASSO sources. However, they did not find any significant amount of neutrinos coming from at least the sources which were greater than 100 TeV or so. Okay, so I come to almost the end of my talk. It's what lies for us in the future. So in future, there would be the multi-kilometer cube neutrino telescope in the Mediterranean, which is the first rings have been already deployed in 2017, and steadily the array is growing. Then there was the proposal for IceCube Gen 2, making it IceCube much bigger. So you can understand that with IceCube right now, we are kind of scratching the surface. There is still a lot of things which we need to do simply because the rate of events is very, very low. So you need to increase the detector volume. So then there was this proposal for IceCube Gen 2, which would be the extended version of IceCube. However, this we recently learned that this is recently kind of currently stalled because no new construction, what NSF has put out or DOE has put up, that there should not be any new construction. But we hope that somehow this impasse will be solved at some point of time. But at this moment, this is currently stalled. In the high energy gamma ray regime, that we need to improve the sensitivities to see some of the sources at higher redshift also and with better sensitivity. So a proposal which has already been accepted and is now going to be slowly going into the construction phase is called the Cherenkov telescope array, which will be an array of Cherenkov telescopes in two hemispheres, both in the northern hemisphere and in the southern hemisphere. One should look at the galactic plane, which is better observed from the southern hemisphere, and the other would look more into the extragalactic plane from the northern hemisphere. The site is La Palma in the northern hemisphere in the Canary Islands, and in the south it's Chile at Paranal. And a partial array of CTA telescopes are going to be ready. The prototype 1 telescope is already ready and is operational at La Palma, and a partial array is hoped to be ready by 2026, because just a few days ago the critical design review of these large size telescopes. So there would be different types of telescopes built to cover different energy ranges, because you cannot cover the energy range from using just one single telescope. So at the lower energy threshold, these are called large, these would have large mirror area, so they are large telescopes. At the medium energies between 100 GeV and few TeV or so, the traditional ones which we have been using over the years. And then at very high energies, you need to have a large collection area to collect even photons. So you will have small telescopes spread over a large area, like kilometer area, a few kilometers area. So this partial array is now getting ready, and so this is the improvement in sensitivity. There would be at least one order of magnitude improvement in the sensitivity to the current generation of telescopes. So we hope to see many more sources, and if IceCube Gen 2 also happens, so we would see many more triggers coming from these in order to do multi-messenger astrophysics. In the Indian context also, we have a telescope in Hanle now built by BRC, the MACE telescope, which is also slowly gearing up in order to make observations of these multi-messenger events. And then we have been also involved with making proposals in X-ray telescopes like AstroSat. With the optical telescope especially, I have been running almost for the last 3 years dedicated optical observation proposal with Himalayan Chandra telescope at Hanle, and also the telescope at Aries in Nainital. And we also submit proposals for target of opportunity programs to AstroSat and all that. But all these, you understand that it requires a very, very tight cooperation between the different observatories, and it's not that easy to do this. So I slowly come to my conclusions that I hope I have been able to at least give you a glimpse of that blazars are plausible sources of very high energy cosmic rays beyond tens of PeV. Of course, they are definitely still not ultra high energy cosmic rays. These are cosmic rays of the order of 10 to the power of 15 to 10 to the power of 17 electron volts from what we see from the energy budget. So the detection of a blazar in flaring state in gamma rays in connection with a high energy neutrino event actually raises many more questions than it has answered. Okay. Main question that came up is, are they really happening during flares or not, when they go up and down or not? What about the temporal? We understand the spatial correlation now well enough, but we do not understand anything about the temporal correlation. So we need to build up statistics in order to understand that. But we currently have a few multi-messenger spectral energy distributions to play it, but it's still very, very model dependent. And as I said, that we need many more such events. We have been performing regular electromagnetic observations, and it's much more important to have tighter cooperation between these observatories to function together. But I say that I believe the future is quite, for the young scientists here, for the young postdocs, PhD students, the future is quite bright in this field, with many more observations to come along. Thank you very much.
And now we have time for questions.
Sorry, I couldn't catch if you said that the neutrinos that are detected in IceCube, are they the primary neutrinos from the astrophysical source? Or
these are associated as of astrophysical origin. So they ride above the background of the atmospheric neutrinos. That's why you go to very high, you have to go to very, very high energies where the flux has actually gone down with a spectral shape of, let's say, 3.7 or so.
So I guess what I'm wondering is it possible that after a scattering there is a very high energy neutrino that still comes out and then detected at IceCube?
The scattering of
some primary cosmic ray with
some intervening. So these are neutrinos. So they would be produced as protons, let's say, get accelerated in the cosmic ray in the sources. If there is matter around, then they would have PP collisions, and then you would. So that's how the correlation study started.
But how about in the intervening intergalactic gas or something scattering on them?
But these high energy neutrinos, I don't think they would be having that much scattering in this. That would not happen. But so that's why the main motivation to look for correlations in gamma rays and neutrinos came up, because of using gamma rays, you could not go and say much more than a certain amount about what sort of acceleration is taking place, whether they're electrons or protons. However, neutrinos start to become the smoking guns, because then if you see correlations between them, you know that these are due to, the gamma rays are due to neutral ions and the neutrinos are from the charged ones. That's it. But these high energy neutrinos, the scattering is much less. Oh, they are always looking, they have a huge amount of atmospheric neutrinos. That's the major. The very high energy ones, how many events? There are quite a few actually. So for example, in this one, let's say when I talked about, for example, like these ones, like when they were doing this study over a period of, let's say, 3, 4, 5 years period study over, they had about 100 track-like events detected, which are of very, very high energies, beyond, let's say, 50 TeV or 100 TeV energy. Yeah, you could have different types. You could have multiplets, which are coincident in certain time window, and you count how much of them. Pardon? So they define it as a kind of a threshold which is of 3 sigma, so that the amount of neutrinos causes a threshold which is, let's say, 3 sigma, and then they immediately sent out an alert. That's the multiplet. And then many of these track-like events are single ones, just one single muon ones. So these ones are, the others are the ones which I was talking about here in the private alert system. Let me go back there. These are multiplets. So these are kind of multiplets. Flares, so these are what you call neutrino flares you see already in the online system, which cross a certain threshold of 3 sigma. And then immediately they send out the alert. But they don't, what they do is that basically, because to take care of the trials, they mute the system as soon as they send out the alert, because they don't keep growing. That's why the how many number is difficult to ascertain. Then the threshold has to fall below the 3 sigma again to the system to become active to send out again alert. They do this because otherwise they would have troubles of taking into account all the kinds of trial factors. Because you have trial factors that self-triggering trial factor also, no? How much of it is self-triggered? Because if you are building up on the same statistics, you are also triggering doing the self-trigger. So that trial factor correction is very difficult to take, as I understand from discussing with them. And that's why they mute the system as soon as they send the alert. And then it falls below 3 sigma, and then again after it crosses 3 sigma, they will send out another alert from the same source. So they have a source list. They keep monitoring the source list, and they do real-time analysis of that. And these are the multiplets. The other ones, which are mostly given out as public, are track-like events.
This galactic plane, I'm a little confused. It looks to be kind of perpendicular to
No, so
equator.
So ice cube is mainly seeing neutrinos from the northern hemisphere.
Correct, yeah.
Because it's in the south. They have some sensitivity to the southern hemisphere, part of the southern hemisphere. And then this is the galactic plane.
Sorry.
This is where the galactic plane is.
Oh.
Around. So this is the way the galactic plane you see is this kind of region.
I'm seeing a dashed line which is kind of vertical. Maybe I'm mistaken.
This one? No. This one.
Dashed line.
So this is what ice cube would see as the galactic plane when they see it from the southern hemisphere, this part. This is the one. Because you are in the south, you are looking in the south, you are looking in the north, and then this is the part which you see as the major part of the south. And then the part of the plane is also the Cygnus region, for example, is in the north, in the northern hemisphere.
Oh, it's not exactly below.
Yeah,
Because of the
part of the plane is also in the north, a very small part, which is the Cygnus region. And then the majority of the part is in the what you see.
So this blizzard that was associated with this event, so it was known from before or after this event you...
The blizzard was known. So there is a lot of data optically, for example, if I show you the long-term here, the long-term curve. So this is the optical data of the long-term optical data over several years actually, and radio data over several years. So the blazon was well known. So it's a Texas source. TXS is basically a catalog where the Texas radio source. And the only thing which we did not know about is that whether it would emit high energy gamma rays or not. As I was explaining, we did not expect it because it was at a higher redshift. So we did not have observations in high energy gamma rays. Whereas in low energy gamma rays, once Fermi became online around 2008 or so, they have been observing low energy gamma rays or medium energy gamma rays from this source. So the source was well established as a source or in electromagnetic spectrum. The only thing which we did not know is that whether it emits in high energy gamma rays or whether it's a plausible source of neutrinos or not. In fact, it was a little bit of a surprise because before this was discovered, most people believed that those sources would be the best candidates where you have a large number of photons around the source because P gamma interaction will take place and produce neutrinos, right? But this source is a much more cleaner source. And that created a lot of excitement that how come these sort of sources which were not really expected to emit neutrinos could emit. It turned out that this source is a kind of a masquerading source. So it has emission lines and a lot of photons, but the jet luminosity is quite high that they masquerade as a kind of a high frequency type of sources. So initially it was not expected, but there are surprises always when you...
So also I wanted to ask another thing, is that what is the probability of identifying a new source with this type of event? Is there...
Okay, that's a good question, but a difficult question is basically because within the ice cube error box, let's say these track events, these are typically of the order of a degree, sometimes better than a degree or so. A new source is, there could be tens of new sources there, especially if you look in optical, because where you have arc second and arc minute resolutions. So you could have many optical sources there. Then, in order to really classify which is your source, you have to do a very thorough likelihood analysis to understand whether they are or not. And but you would expect that those sources to also emit high energy gamma rays or X-rays. They may be quiet in gamma rays simply because the environment may be killing the gamma rays down, but then they would at least see it in X-rays or so. So that's where the motivation of preparing the source list comes. You take into account all this available multi-wavelength information in order to prepare a list which would be the most plausible sources. IceCube also looks for all sky events and looks for unknown sources also. But these are mostly because there you are swamped by your trial factors. Because the whole sky you have to account for your trials. Here, since you have a source list, your trial factors are less, and hence your significance will be boosted.
Okay. So you mentioned about this leptohadronic and photohadronic models to model your photon spectrum. Can you say about what is the process that it is trying to model?
So basically these are P gamma and PP interactions, and then there are
what is leptohadronic?
Oh, so you try to so there are also electrons in your system, and so it's not a pure hadronic model. When you call it a leptohadronic, it means there are electrons and protons in your system. You then try to understand what is the contribution of electrons and what is the contribution of hadrons to the emission, the high energy emission that comes. So the leptonic emission would be through synchrotron and inverse Compton. Whether that is the dominant emission, then you of course do not need any neutrinos to fit your data. If you would need neutrinos to be there along with this photon emission, then you would need to have a dominant proton contribution along with your electrons. They are there, of course, because in cosmic rays, of course, the main question is that 98% of them are protons. Only 1% of electrons, but most of the cases we see gamma ray emission, but we did not see neutrino emission. There are two cases. One, we have an observational bias. We are always looking for such sources where you see electrons mainly. And then, of course, neutrinos are hard to detect. So once we start to detect many of them, then we can play this game better.